All right, so let's highlight the most important part here again. Um, to graph, well, in this case, so to graph y equals f of b, f of 1 over b plus x, multiply all x coordinates by b. And on the other hand, when we see the number multiplying, we do the reverse to divide. So to graph y equals f of bx, divide all x coordinates by b. So in this case, it's the reverse. This is going to affect the horizontal scaling affects the x coordinates, not the y coordinates, as opposed to what is that? The vertical scaling. And let's do one example to illustrate this idea. Okay. I really don't want to create. I don't know if I. Well, actually, let me do it. Let me create a table for the function absolute value of x, and I'm going to do it on the side. Okay, so that'll be okay. Absolute the function. Okay, for x, and y will be absolute value of x. Right. So y equals the absolute value of x. Well, x, I don't want to do like -3, -2, -1, negative 1, 0, 1, 2, 3. Let me do -4, 0, and 4. That's going to give us, well, only 3 points, but at least it's going to give us a good window image here. Well, so if we take the absolute value of -4, that equals to 4. If we take the absolute value of 0, that equals to 0. And if we take the absolute value of 4, that equals to 4. That's going to give us the order pairs. Number 1, 0, 0, -4, comma 4, and 4, comma 4. All right. So let's draw the graph. And it's the graph that looks like the V-shaped, the so-called V-shaped graph, right? The absolute value. All right, so now let's get into the points, to graph the other two functions. So again, let me highlight the function with blue. The original function is highlighted with blue. And then, well, let me use green for the second function, g of x. And g of x will be scaling the x's by a factor of 2, which in this case, well, so for, okay, let me go down below the graph. For g of x equals to the absolute value of 2x, in this case, divide the x coordinates of f of x equals absolute value of x by 2. Right? So let me start with that. Let's see. Let me write down the coordinates. And that'll be, okay, what was that? -4, comma 4, 0, 0, and what was that? 4, 4. All right, so it's the x coordinates, the ones that get divided by 2. All right, so let's see. Divide by 2, divide by 2, divide by 2. And well, this will become -4 over 2, that's a -2 comma 4. And then 0 times 0 divided by 2, it's still 0. 0, 0. And 4 divided by 2, 2 comma 4. All right? So it's 2 comma 4. So let's plot those points. Let me use the color coding here. Okay, so that's going to be -2 comma 4. Okay, -2 comma 4, that'll be that point. The second point again will still be the origin 0, 0. Let me plot it. And 2 positive 4. So that's going to give us this graph actually. Which, doesn't that graph looks horizontally scaled, horizontally not stretched, compressed? All right, let's look at the form of the function. It looks like, okay, so horizontally, shrank or compressed or contract, so compressed, which is what we did for the second part of the process. Well, let's verify this using our graphing calculator. This time, rather than seeing the three graphs at the same time, I'd rather rather you guys see one at a time so you can see how it's gonna work. All right, so let's see. So let me clear all this. Okay, nope. Second quit. Clear. Okay. Let me clear the history. Let me go to the graph. Okay, and again, if you have something, make sure to clear it. And well, what we're gonna have here, number one, we need to type the absolute value function. Recall that we go to math, num, and then the first option, ABS, the app stands for absolute value. Click enter and type X. So that's going to be our function here. And well, the second function is, what is that? Math, num, apps. Let's put 2X. All right. And well, what we're going to see the original graph and the second graph. Do you see how the second graph is actually horizontally compressed? All right. Let's do the same with the third example. So for the third example, let me use a different color first of all. Okay, so that'll be, so let me highlight it as well. So that is 1/2 x. All right, so let's see. Now, for h of x, h of x equals to absolute value of 1/2 x divide, or rather no, multiply this time. Multiply the x coordinate of f of x equals to the absolute value of x by 2. Right? That is, I'm going to start with, in this case, what's that? The points on the original function that I chose in this case, -4, 4, 0, 0, 4, 4. I could have used more points, maybe like -2, 2, and also 2, 2. But I think 3 points here are more than enough to give us a good picture of this function, by the way. All right, let's see. So, okay. So what about multiply both sides? Okay, no, not both sides. Multiply the x coordinates by 2. So multiply that times 2, that times 2, that times 2. That's going to give us a whole new set of order pairs. That is -8, comma 4. The y's remain the same. 0 times 2, that's still 0, 0. And then 4 times 2 is, what's that, 8, right? So, comma 4. And let's plot this point using a different color, same color I had over here. Okay, so that's a negative 8. Well, actually, the negative 8 is going to go all the way out, comma 4, somewhere here maybe. And then, what is that again? 8, comma 4. So that'll be all the way here pretty much. So that's going to look like this. Do you see in this case how this graph is horizontally, well, stretched, not compressed? It was actually stretched horizontally. It got wider. That's another way to describe it. Wider, more stretched, or what else? There's other words over here. Expanded, dilated, Okay, let's put it in the graphing calculator to see what we get. And again, go math, num, apps. Oh, hold on, second quit. Okay, so math, num, ABS, that's gonna be 1/2 x. And graphing, well, that's the one in black, and that indeed, that's actually confirms our idea, right? Okay, so last time I also mentioned that the compression, stretches, and all that are a little tricky. And let me talk about let me tell you why. Okay, let me use that same example for the absolute value. Let me do. Okay, you guys might want to use the back side of your page so you to write this down. I'm just going to add another blank page here to go about it. All right. Okay. So so here is the thing. The transformation. Okay. Hmm. The transformation from okay, y, okay, the same function, f of x equal to the absolute value of x to from f of x to absolute value of x to g of x to equals to the absolute value of 2x. All right. So we want to do that, and the thing here is can be interpreted in two different ways. What are those two different ways to interpret this transformation involved? Number one, um, as um, as a horizontal scaling. Number one, as a horizontal, and B, letter B, as a vertical scaling. Either way, you might wonder why. I mean, it's not like, okay, here's the thing. It's not like in the what you call in the vertical shifting or the horizontal shifting. Well, there's no way to confuse those two. I mean, one is going in the x direction, positive or negative, and one is going, and the other one is going up or down. However, when it comes to the scaling, it's a little weird because for the horizontal scaling, and let me repeat the same exercise right here. So. And again, let me do the whole analysis again. Okay, so to graph g of x equals to absolute value of 2x, as a horizontal scaling, we would need to divide, what's that?
The x.
The x coordinates. Of f of x equals to the absolute value of x by 2. All right, that's what we just did in this first example we're discussing. But I'm going to repeat myself here so we can put it together with a different way to go about it. All right, so here is the thing with how would we do it with the vertical scaling. Well, doesn't that quantity inside of the absolute value bars look like a product between two quantity, the product between 2 and x? Okay, so how about we use the properties of absolute value expressions to simplify, well, to rewrite it. So how about g of x equals to 2x, and that equals to, oh, isn't that the absolute value of 2 times the absolute value of x? But what's the absolute value of 2? Isn't that just 2? All right, so that's g of x um, That equals to 2 absolute value of x. Now, did you see that the coefficient is multiplying outside of the function? Looks like the a times f of x. So in this case, um, the other way to do it is, so to graph, what is that? To graph g of x rather. G of x equals to 2 times absolute value of x multiply, in this case, the y coordinates of f of x by 2, right? In this case, we would multiply the y coordinates by 2. Okay, how about we do that by hand? Let me bring down the same coordinates I started with. Well, actually, I'm gonna come up with a nicer set. I'm gonna do instead. Okay, I'm gonna do from -3, 3, 0, 0, and 3, 3. Over here, I'm gonna use the same coordinates: -3, 3, 0, 0, 3, 3. Sounds good? All right. So what we're going to do, divide the x coordinates by 2. Oh no, never mind. I have to do the 4 again because it's not going to be divisible nicely. Never mind. Sorry about this. Now I remember why I was doing the -4 to 4. So 4, 4. Okay, change to 4, 4. Yes, we want to deal with nice numbers, right? So let's make it practical and easy to go through. Although in some cases, don't get me wrong, there will be times in which there will be no way around. We will have to deal with fractions, and when it comes to plotting those points on a grid, well, you will need to have a sense of of scaling each of the marks in the Cartesian plane. All right, so what we're gonna do here? Let's divide by 2, divide by 2, divide by 2. And over here, but that, okay, notice we're dividing only the x coordinates. On the other hand, we are, multiplying the y coordinates by 2 times 2 times 2 and times 2. All right? Okay, let's get the new set of order pairs. So divide, divide, divide. So that'll be, okay, so -2, 4, 0, 0 still, and 4 divided by 2, that's 2, 4 remains the same. And then for the other operation, to multiply by 2, that'll be, all right, so -4, 8, 0, 0, and 4 times 2, that's 8. All right, so let's see what we get when we plot these 2 points. Right, I'm going to draw a Cartesian plane, and check this out. Okay, I need to scale it. 1, 2, 3, 4, 7, 8, 9, 10. 1, 2, 3, 7, 8, 9. 2, 3, 4, 5, 6, 7. Oh, I need one more, right? Oh, that's fine. That's fine. Okay, so let's plot these 2 points. I'm going to use green to plot -2, 4, 0, 0, and 2, 4. So -2, 4, that'll be here, 0, 0, and 2, 4. All right? So that's going to give us this V-shaped graph, all right? What about these points right here? Can we plot? Can we use a different color? And well, in this case, I'm going to do -4, 1, 2, 3, 4, 5, 6, 7, 8. Oh, that's actually this point, and it's also on the graph in green, isn't it? So that's 4, 8. Same here. I wonder why is that? because it's the same function, isn't it? So again, it doesn't matter. So that's what I wanted to show you here. I want to show you how a vertical scaling can be exactly the same as a horizontal scaling. For instance, well, the only difference is that if we treat the function as a vertical scaling, well, um, what we do in this case is do the operation on the y coordinates. If we wanted to treat it like a horizontal scaling, we do the transformation on what is that on the x coordinates. And well, now that you have seen this graphically, let me give you other examples without graphing, but just by analyzing the type of function here. All right, for instance, okay, let me give you a couple examples. Okay, so letter A. How about y equals the square root of 4x? All right, let me just keep it the square root of 4x. That's fine, right? So there's two ways to go about it. Number one, which by the way, how about we simplify this function a little bit? Do we agree that in this case we have the radical of a product, which is the same as the product of two radicals? That is equal to the square root of 4 times the square root of x, which equals to 2x. Okay, the square root of 2 root of x rather. All right, so here is the thing. I'm going to treat this guy right here as horizontal scaling, and I'm going to treat this guy as a vertical scaling. All right, I'm not going to do any plotting points, any creating of of this or new order pairs. I just want you to see the forms of the function so you can interpret them one way or another. I'm going to do a few of this so you can get the whole gist of this. All right, so number one, let me treat this. Oh, let me change color real quick. Let me change this to green maybe. Yes, it'll be good. All right, so y equals the square root of 4x. Okay, well, hold on. More properly to graph the square root of 4x. So in this case, we will divide the x coordinates of y equals to the square root of x. All right, or else rather, if you want to visualize this as a vertical scaling, then to graph to graph 2 square root of x multiply the y coordinates by 2, and in this case, oh, I forgot to divide by 2. The y coordinates of y equals square root of 2, square root of x, also by 2. All right, so those are the two ways to go about the graphing of this function. Let me do another example. How about yes?
First line, the x coordinates of y is equal to 1 under root x. So is it now 4?
Yeah, so we divide by 4. Yeah, my bad. Yeah. Let me do another example without the silly mistake. Okay, so let's see. So letter B, for instance, y equals to 1/3 x cubed, for instance. All right, 1/3 x cubed. All right, so in the end, isn't this the same as saying, yes, isn't it the same as 1 over 27 x cubed, right? It's the same thing. Now, here is the thing. This guy right here, the first version, I'm going to treat it like a horizontal scaling. And this guy right here, I'm going to treat it like a vertical scaling. Okay, one thing I forgot to write on the previous exercise is to identify the parent function. I mean, I said it over here anyway, but let's just do it from the very beginning. Y equals the square root of x. All right, so over here, the parent function looks like, what would that be? X cubed, right? Y equals to x cubed. Okay, so x cubed will be our parent function. Now, going with the guidelines to plot or to graph or transform a graph with the form 1 over b inside parentheses. Let me go way back. Okay, let me go way back. Where is it? Oh, right here. So f of 1 over b multiply, all right? Multiply, so in this case, we will multiply by b on the x coordinates only. So to graph, one third x cubed multiply the x coordinates of what is that, of y equals x cubed by multiply by 3. All right, that's one way if we see it as a vertical, I mean as a horizontal scaling. However, on the other hand, so to graph 1 over 27 x cubed divide the y coordinates by 27. Right? So we divide by 27 if we see it in the perspective, you know, like as a vertical scaling. But if we see it as a horizontal scaling, then we would need to multiply by 3. Right? And again, that's the reason why this kind of transformations when it comes to scaling, they're a little tricky at times. Like, wait, what are we doing? Are we doing vertical stretching or are we doing horizontal? I mean, vertical scaling or horizontal scaling? Well, it depends on how you want to see it. Do you want to do horizontal scaling? Well, make sure to see it one way. You want to see it the other way around? Make sure how it works. The division or multiplication of one of the coordinates or the other. All right, and with this we finish the first part of the section. So okay, the next part will be applications of more than one transformation at a time. However, before doing that, well, I want you guys to see the very last page of your of that handout. This last page has all the information you need to know. I mean, it's essentially the summary. Like, oh wait, does that look like something plus or minus a number outside of the parentheses, outside of a radical, outside of absolute value? Oh, that means vertical shift. Either go up or down. All right. If it's up, I mean, if it's a plus, it's up. If it's minus, it's down. So again, the vertical shifting go in the direction of the sign that we have. And well, I have described right here what to do with the coordinates, and then specifying here, and it's specifying here what coordinate gets transformed, right? Horizontal shift. Let's review it again. So when you have some a number inside, the parentheses adding or subtracting. Well, if it's adding, what do we do? Remember, we do the reverse, which is to subtract h units to the x coordinates. This transformation, the horizontal shifting, affects the x coordinates, and well, we can see it in the summary how it is specified that it is the x coordinate that gets changed. And then we moved on after looking at vertical shiftings and horizontal shiftings. Then we moved on to the reflections. And well, there's two kinds of reflections. Reflections about the x-axis, which is the first one, all right? That is to multiply the y coordinates by -1. All right, and then we have the reflection about the x-axis, the vertical, and the y-axis is actually acting like a mirror in this case. And well, we will see the points reflected on the other side of the y-axis. And well, here it is, the vertical scalings and horizontal scaling. And in this case, again, a vertical.
Professor,
Yes.
sorry, for reflections, I'm having trouble distinguish the difference between them when they appear in an equation.
Uh-huh.
I was wondering, maybe point out an example in calculus.
An example? Sure. Let me make something up over here. How about that? For instance, let me do, okay. Okay, how about the same one we did in class? Like y, so the parent graph y equals to the square root of x. Okay? So y, no, let me call it f. F of x, square root of x, g of x equals negative the square root of x. That will correspond to the negative in front of the function, right? And h of x equals the square root of negative x. That'll be the negative inside the function, right? So how about we use the graphing calculator to see these two? Okay, so this one will represent, okay. Okay, let me put them here, okay. So reflection across, what's that, x-axis, and reflection across the y-axis, all right? So that's what we should be seeing when we graph two at a time. So the first one is just the parent graph, right? So parent graph, and then reflected across the x-axis. That is, it's flipped upside down, right? In a more known mathematical language here. And the last one, it's reflected across the y-axis, right? Let's go to the calculator and type these three functions again. Okay, let's see. So I'm going to go calculator, y equals, if you have anything, just clear it. And let's see, so second square root of x, all right? So that'll be the parent graph we know, right? Well, we can already identify. I'm going to go back to y equals to type the second function, and be careful. I'm going to make a mistake here, which is the most common mistake a lot of students do. Check this out. I'm going to put this minus second square root of x, and I'm going to click graph. And I got a syntax error. Any ideas what did I do wrong?
Yeah, put negative instead of minus.
Actually, the reverse. I put the minus to subtract instead of the negative. Oh, second quit instead of the negative. So in this case, This minus I put in front of this radical. It's the subtraction symbol, which is below the multiplication and above the addition. So that's the wrong negative you will put in there. The correct one, it's the one that you have next to the enter and next to the decimal point. So make sure to change it to that. So what is that going to be? So here we would expect to see the parent graph and which one? The one that it's reflected about the x-axis. Hopefully that's the case. There it is. All right. Or it's flipped upside down, and that's another way to say it. And lastly, what's that? Square root. Second square root of, again, make sure to have the correct negative and x. All right. Graph. And now see how it's reflected across the y-axis with respect to the blue one. My pleasure. Okay, let's see what else can we do about. Okay, let's see what's next. So, again, and so here is the summary. So when you're doing your homework, when you are coming up with new exercises, this is your best friend. This summary right here is your best friend. So the minute you identify a function, okay, identify the parent graph first. Well, get some of the key points on the graph, right? Like, for the radical function, for instance, recall that we always use points for which the x coordinates are nice numbers. What do we mean by nice numbers? Numbers that have a perfect square root. Those are called perfect squares. Do not just make a table of values 1, 2, 3, 4 because you're gonna get some decimals for some of those. For a parabola, pretty much any number works. Maybe a range between -3 to 3. It's a good range. For a cubic function, maybe from -2 to 2. That's more than enough. All right, let's see what's next. There's much that we will do about it. By the way, okay. So we're done. What we have done so far is we're done with all this, with describing the different transformations. Now let's put these transformations in action and construct new functions by taking into consideration one at a time. And that's example number 6. So for example number 6, they're asking us to find the function that is finally graphed after the following 3 transformations are applied to the graph. What's that? Absolute f of x equals absolute value of x. Okay, so number 1, part A. They're asking us to shift the graph to the left by 2 units. What would you do to this function so it looks like it is shifted 2 units to the left?
So you would write f of x equals inside of the absolute value brackets x plus 2.
Okay, so f of x equals absolute value of x plus 2?
Yes.
All right. So yes, it's to the left, and we go with the opposite sign as a direction. Left means plus in the function. All right, which would subtract 2 units to the which coordinate? The x coordinate or the y coordinate? The x coordinate. Good. Letter B. Shift up 3 units. What would you do? How would you modify? Okay, this function we have so far. What would you do so that it is now on top being shifted left 2 units? Now it's being shifted 3 units up.
Outside the absolute brackets, add 3.
At 3. F of x, positive or negative 3?
Positive.
Positive, all right? Again, because vertical shifting goes with the sign positive 3 and negative down. Yes, that's a 2, right? Yeah. Reflect about the y-axis. All right, what would you do to reflect about the y-axis? So what coordinates, number 1, check this out. What coordinates get affected when you reflect about the y-axis? Are they the y coordinates or the x coordinates? The x coordinates. So what would you do to see this reflected, no pun intended here?
Multiply by -1.
What do we multiply? With dx, right? So that'll be f of x equals to absolute value of negative x plus 2 plus 3 outside. All right? So what we're doing here is describing one of the functions, I mean one of the transformations at a time. All right? All right, let's see. Graphing functions using transformations. I don't want to get into the graphing functions using transformations just yet without first making sure that we understand how every single number affects on a parent graph, you know. So what I'm going to do here, check this out. Let's see. Okay. Yeah, we'll get back to this later, okay? So let me go back to the, well, in your case, guys, go to the back side of the page. I'm going to create just another blank. And I'm going to come up with just random, you know, random examples. So, all right, let's see. So that'll be letter A. Okay, so for letter A, how about, okay, number one, first of all, the instructions. Okay, what are we going to do? Given the functions below, describe all the transformations in words. Okay, let me start with something simple, just to, you know, okay. In words, by stating or mentioning somehow the parent function or their parent function. All right, let's see about it. Let me make something up. So let me do. I think I'm just going to be using g of x and h of x because we will always refer. Typically, we refer to as f of x to our parent function. All right, let's see. So g of x on letter A. G of x equals to the square root of x plus 3 minus 7. All right, let's have a look at this function. Let's see what transformations do we have. However, first of all, what's the parent function?
F of x is equal to square root of x.
All right, function. Parent function, f of x equals to the square root of x. Sounds good. And again, so here is the thing, guys. Regardless of the function you were given, whether this is f of x equals to the square root of x, the cube root of x, x squared, x cubed, you name it. Doesn't matter. Or 1 over x, it really doesn't matter. So the transformations will be described exactly the same way. All right? So let's see. Parent function transformations. So what are the transformations we have over here?
Subtract 3 units from the f of x coordinates, x coordinates.
All right. Well, not in terms of the addition, subtraction. I mean, like left, right, up, down. In those terms, I forgot to mention that part. But I mean, technically, you're right. You're right. Yeah, you're right.
It would be to the left 3, down 7.
Okay, so transformation. That means shifted 3 units to the left 7 units down. All right. Let me do another one. Let's do another one. That is letter B. H of x equals, I would like to do yes, negative x plus 5 cubed minus 11. Well, let me know, not minus 11, maybe plus 4. All right. All right, let's have a look at this one. H of x equals negative parentheses x plus 5 quantity cubed plus 5. All right, number 1. What's the parent function here?
X cubed.
Parent function. F of x equals x cubed. X cubed, And well, what's next? The transformations. The transformations. So what transformations do we have here?
Shift to the right 5, up 4.
To the right 5, up 4. Okay. Yes.
Don't you reflect across the x-axis first?
Reflect across the x-axis. Well, that's fine. So reflected about the x-axis, comma, what else?
And then it'll be to the left 5 units.
To the left 5 units
Up 4 units.
and up 4 units. Shifted to the left 5 units. And lastly, shifted up. What's that? 4 units. All right, shifted up 4 units. How about we see these graphs actually, so we can, see all these words, in action, So let's see. Let me erase. Well, actually, I'm going to clear the last two because we are going to need the square root function. That is, I'm going to do another square root of x plus 3 and then minus 7. So second square root of x plus 3 and then minus 7. All right, and graph. Okay, you can always use this first point, the origin, as your reference point because again, shifting 3 units to the left and then 7 units down, it's like dragging the graph from the origin and move it. Okay, 1, 2, 3 units to the left, and then 1, 2, 3, 4, 5, 6, 7, and well, here we can see it on the graph, right? Let's look at the second example using the graph, right? And well, so that is okay. First of all, we're going to plot the graph of x cubed, and then. What is it? That's going to be negative, open parentheses, x plus 5, close parentheses, raised to the third, and then, what is it? That's add 4. All right? Okay, let's see the graph. That's going to be the original graph. So number 1, yes. Do you see how in this graph, the graph in red, first of all, it was reflected about, we said, the y-axis, right? So that is flipped. It looks flipped upside down. And then on top of that, we're dragging that graph. What is that? 5 units to the left and then 4 units up. Does that look like it? So 5 units to the left, and then 1, 2, 3, 4 units up, right? So indeed, this checks whatever we have done by words. All right. Okay. Yeah. So in this case, doesn't that look like we are doing two operations on the x? What are those two operations we're doing?
You're gonna, of your parent function, you're gonna take x and divide it by 5.
Uh-huh.
You're also gonna move it to the right for
3 units. Okay, now here's the thing. Which operation do we do first? All right, that's the question. Which one do we do first? We are going to go with the PEMDAS operations, right? So in this case, here between x and 5 we see a multiplication, and between the x and the -3 we see a subtraction. Which one goes first, the multiplication or the subtraction in accordance with the PEMDAS rule? Multiplication, right? So, okay, let's see. So, parent graph. Parent graph, that is f of x equals to x squared, simply x squared, right? Okay. And then from here, well, let's describe everything about horizontal shifting. So number one, okay, so horizontally, transformations. Horizontally, what is that going to be? Horizontally, and it's going to be compressed, right? Because in the end, I think you can already envision the operations we're going to do, which is in this case to divide the x's by 5, right? So that when we divide x's by a number, that actually scales them to make them tinier. That is a skinnier function, if you will. That'll be, or rather compressed, horizontally compressed by a factor of 1/5, right? Because we're going, so here is the thing, we're going to divide the coordinates by, the x coordinates by 5, or multiply them by 1/5, which is the same thing. And then what's next? Shifted, what's that? Shifted 3 units, to the right. Right, shifted 3 units to the right. And well, it looks like we're done with this, right, with the horizontal. Now let's look at the yellow ones, the ones that describe any vertical, either vertical shifting or vertical scaling. So now it will be vertically scaled, compressed, vertically scaled. Actually, vertically would it be stretched, right? Because we're multiplying by a number larger than 1. Vertically stretched by a factor of 2. And what about that -4? What is that going to tell us?
Shift the y down 4 units.
Shift it four units down. All right. How about you guys try one? Let me pause the wall. Let me write it down. And let me pause the recording, and I'm gonna make it even more interesting this time. You'll see. Actually, for the next one, I will pretty much add every single transformation. How many are they? 1, 2, 3, 4, 1.5, the six transformations in one single exercise. So you can get an idea whether you got the whole gist of this. All right, so let's see. Letter D, all right, so that'll be h of x. That'll be negative 1/3 square root of, what's that? Let me put negative 1/7 x plus 4, and then plus 5. All right, there you go for it, all yours. Okay, so for h of x equals to negative 1/3 square root of negative 1/7 x plus 4 plus 5, let's see all the different transformations. And again, don't let all this madness scare you. Again, divide the problem into two parts. Number one, everything related to the horizontal translations or horizontal transformations, which is the quantity inside of the radical, that is the negative, what is that? Highlighter. Negative 1/7 x plus 4, and save the rest for the outside. Negative 1/3 plus 5. All right. So let me do, well, number one, let's identify the parent graph. That is parent graph. Whoops. What's a parent graph, first of all?
F of x over x.
Square root of x. And okay, transformations. Let me start with transformations. Let me start with the inside of the radical. That'll be, what's that? The negative 1/7 x plus 4. So number one, it's reflected about the, what is that going to be? The y-axis first, right? That is because when we change the sign of the x, that sends it to the other side of the y-axis, right? So reflected about the y-axis, and then horizontally, will that be compressed or stretched this time? Stretched, right? By a factor of 7, right? And what about that plus 4? What is that going to do? 4 units and shifted 3 units. 4 units to the left. All right. Okay, so we're done with the x transformation. Let's have a look at the y transformation. So number one, the negative sign outside of the radical. What does that mean? The one in yellows, the negative?
Reflected cross x-axis.
Reflected across the x-axis. All right. No, the x-axis. Yeah, that's true. And then what else? In this case, that 1/3 would mean, well, it's vertically. That's vertically. But is it vertically compressed or vertically stretched?
Compressed.
Compressed, right? By a factor of, what's that? 1/3, right? And lastly, what about that plus 5? What is that? I mean, yes, they were added. Well, we're going to describe the math operations in a second. But yes, what is that going to do? Up 5 units and shifted up 5 units or 5 units. All right. Okay, let's sketch. I mean, not by sketch. I don't mean to sketch the graph. I mean just the process to get the how would we graph the function. We're gonna get into an actual example soon. So number one, what are we going to do? Well then, okay. So let's see about it. Okay, so to graph. The graph h of x equals to -1/3 square root of -1/7 x plus 4 plus 5. Okay, number one. Okay, starting with the x coordinates. All right, with the x coordinates, let's see. What are we going to do? Well, let me use blue. Let me change also for blue, just so we can see. I don't know why I changed color. Anyway, so number one, or letter A. In this case, how about? Let's do the 1/7. Does that mean divide the x's by 7 or multiply by 7? Multiply by 7. However, we can do the negative at the same time, right? So how about multiply by -7? So that takes care of 2 operations at a time, because I mean, yes, you can do the multiplication by 7 and then multiply everything by 1. So, but in this case, I don't think it's too crazy to do 2 operations at the same time, that is to multiply by negative at the same time. So multiply the x coordinates by -7, and then subtract four from the resultant x coordinates. So that's going to do it for the x coordinates. Now let's talk about the y values. So for the y values, what would we do? How about do we multiply? Do we divide by 3 in accordance to the 1/3?
You could divide by -3.
Divide by -3, right? So we take care of the 2 operations at the same time. So divide the y coordinates by -3, or multiply by -1/3, all right, either way. And then add them 7 units. Sounds good? Because oh wait, where did I get the 7 from? No, that's actually 5 units, right? 5 units. Yep, that'll represent the vertical shift. No, we're not going to do this crazy one, because check that out. Division by 7, that's going to get us the really, really crazy numbers. I just wanted to show you how, number one, the transformations read in words, and then how do they read mathematically in accordance with all the descriptions we did for every single transformation. And then what's that? And then how do what math operations we do, which again, what we did right here in part A and B as the sketch of how we would get the graph of that function. That's based on the summary you have at the very end of this handout. All right? How about we put all this in action and we do one that actually we can graph without getting too crazy numbers. All right, so let's go back to page. What page is that? Okay, example number 7 on page 5. Okay, so graphing functions using transformation. So, well, this order may be altered, but I mean, usually we do the horizontals and then reflection. This order actually is wrong. Let's just well, I don't think it, I mean, it's not wrong, it's just not in the order I would have wanted. Just scrap that part and actually let's follow the order we sketched earlier in the previous example. All right, so let's graph each function using transformation techniques. Starting with the graph of the basic function, and be sure to show at least 3 key points. All right. So number 1, we have f of x equals 2 times quantity x minus 4 quantity squared plus 3. Number 1, how about we identify the parent function? What's the parent function? X squared, all right? So y equals x squared, it's our parent function. And we know the y equals x squared, that goes 0, 0, 1, 1, 2, 4, 4. Where all the way we went? Okay, 3, 9, and 4, 16. All right. So and then negative 1, 1, negative 2, 4, negative 3, 9, negative 4, 16. All right. Let's go about drawing that parabola. And let's see. So, all right, so let's describe the transformations in words. First of all, again, let's take into consideration the inside first, that is the horizontal shiftings, the horizontal transformations rather, not just shifting. There could be, well, that's only a shifting, a horizontal shift. And then the outside transformations, which are the vertical transformations here. All right, let's state them one at a time. So number 1, this is f of x. Okay. F of x equals to 2 times x minus 4 squared plus 3 is x squared. Number 1. Okay, what about the inside of the parentheses? What do the x minus 4 tells us about? Shift to the right, how many units? Shifted 4 units. Right. To the right. And what else? Well, okay, we're done with the horizontal transformation. There's only a horizontal shift. All right. So what about the transformations in yellow? What are we going to do with the 2 and then the plus 3? Which one do we do first? Do we do the plus 3 or do we do the 2? The 2 first, right? Pam does multiplication first and then addition. Okay, so what is that 2 going to do?
You're going to vertically stretch by a factor.
Vertically stretch. Stretch by a factor of, what's that? A factor of 2, right? And lastly, what do? What about the plus 3? Shift it 3 units up. Okay, let's start with them. Okay, I'm just going to take 2 key points. I'm going to take the following key points. All right. Let me change this to blue again. The graph. I think it's easier. I'm going to take the points -2. Check this out. -2. -2 4. What else? 0, 0. And what else? 2, 4. I will only use those 2 points as a reference to shift the graph. All right. Okay, so the first thing we do, okay, let's go with the horizontal shift. That is 4 units to the right. What mathematical operation do we do for 4 units to the right?
X plus 4, that's 1 plus 4.
So x minus 4, well, that represents the 4 units to the right, but what operation do we do on the order pairs? Add 4 to which ones?
X.
To the x values, right? So add 4. Oops. So plus 4. Oh, that was not. Oh, perfect. So plus 4, and plus 4. All right, that's going to give us a whole new set of order pairs. All right, so that'll be 4 minus 2 equals to 2, comma 4. 4 plus 0 is 4. 0 is still 0. 4 plus 2 equals to 6, comma 0. All right, so that's the first operation, and that's all about this transformation in the horizontal direction. There's nothing else in horizontal transformations. And now let's take care of the vertical transformation. So that is vertically stretch it by a factor of 2. What are we going to do in this case mathematically?
Multiply the y coordinates by 2.
Multiply the y coordinates by 2. All right, so times 2, times 2, times 2. All right. When did I have a 0 here? That's supposed to be a 4, right? Okay. So that'll give us the following order pairs. The x's remain the same. 4 times 2 equals to 8. 4 comma 0 times 2 equals to 0. 4 times 2, another 8. Sounds good? Okay. So we're done with, okay, let me highlight one of the every operation. So we did the shifting of the 4 units to the right by adding 4, all right, to the x coordinate. Sounds good? Then we did, what's next? Vertically stretched by a factor of 2, which implies multiplication of the y's by 2, all right? And then finally, what are we going to do? The shifting 3 units up. What do we do in that case?
Add 3 units to the y coordinates.
Add 3 units to the y coordinates. Okay, let me do plus 3. Whoops. Plus 3, plus 3, and plus 3. That's going to give us the following order pairs. All right, so that'll be, okay, new set of order pairs. That's a 2, comma 11. 4, comma 3, 6, comma 11. All right, let me highlight this operation with a different color. Let me use, no, maybe not a yellow, maybe not, well, maybe blue, purple. Shift 3 units up. That's the plus 3, plus 3, plus 3. Sounds good? And we're done with creating the new points for the transform function. Now let's use a different color to plot the graph of that function. Let me use green. So, okay, so I'm going to go 2, comma 11, and then 4, comma 3, and then what's next? 6, comma 11. And that's going to give us this parabola right here. Looks like this. Whoops. And looks like that. All right? Okay. Does that graph in green look like shifted to the right? Does that look like it is shifted up? Does that look like vertically stretched? Now, here is the thing with the vertically stretched. A vertically stretched means the same thing as horizontally compressed, right? Okay, let's see this graphically. So, graph, clear. Oh, wait. Okay, clear. So that'll be first of all x squared. And what else? How about, okay, that is, what was that? 2 parentheses x, what is that? Minus 4 plus 3. Quantity squared. Whoops. What the hell am I doing here? Delete. Okay, squared and then plus 3. Alright, let's graph both of them. And I mean, of course, the graphing calculator is going to do it better. But by the way, actually, we need to be careful with the calculator because although they're very smart devices, they help us do a lot of calculations, get a lot of pretty cool graphs. Well, it could be a bit deceiving at times because very often times it may look more symmetric than we would like because that's because of the aspect ratio of the graphing calculator screen, which is not perfectly square, it's actually rectangular. You see the marks along the x-axis, they're larger than the marks along the y-axis, so that's why the graph might look a little bit smashed rather than the original aspect ratio. So just keep that in mind. Actually, when you get to graph circles, they're not going to look like circles. They're going to look like ovals, like ellipses, but in this case, smashed horizontally. All right.